Thank you very much. It's wonderful to see so many of you. I've got, well, half an hour, a bit less now, to talk to you about electrical and electronic engineering. So it's always so pleasing to see lots of people come to an electrical engineering lecture. I'm not going to teach you about building race cars or jet fighters or anything like that. I'm going to talk to you about some core electrical and electronic engineering. Okay? So I'm going to start talking about inductors, a fundamental electronic component, and then I'm going to move on to the application of magnetic fields in a practical case of magnetic brain stimulation. So what we're first going to do is meet the inductor and learn its current voltage characteristics, or what we call the IV characteristics of inductor. I'm sure most of you know, for example, the IV characteristics of a resistor. Inductor is a similar two-terminal component. We're going to understand, or we're going to look at briefly, how magnetic fields interact with electric current to form an inductance, although we're going to cut this short because it would normally be a part of a sort of 2-hour lecture block. And we'll see sort of how we use a coil of wire to create an inductor, and how we can then transfer the understanding that we build up from sort of fairly basic structures to more complicated systems, like, for example, the brain, which we'll come to in the second half of the lecture. So basically, the start of this lecture you can think of as being a true taster lecture, because it's basically lifted directly 1/3 of Lecture 6, Inductors, from P2 Components and Circuits, which is something you'll study in your first year if you come and do engineering science here at Oxford. So it genuinely is a taster lecture, or at least part of it is. Okay, so we introduced the inductor in the first slide. It's a two-terminal component. Many of you have probably seen, this, excuse me, let me change that to a laser. Otherwise it's going to get very confusing. Here we go. Pardon me, should have turned that. There we go. Right, so this two-terminal component here. A two-terminal component has a voltage across it between the two terminals on the left and the right, and has a current that flows through it. Now, the fact that this thing is an inductor means that the relationship between these two quantities, the voltage and current, is expressed by this equation. Right? So it says the voltage across it is equal to the rate of change of the current flowing through it, the rate of change, di by dt, multiplied by its value, inductance in this case, L. Inductance is measured in henries. Nice name, and that completely describes the behavior of an ideal inductor. Of course, if we have a differential equation, we can turn that into an integral by flipping it around, right? So we can say that the current that is flowing at any time t here is equal to some initial current, traditionally we take that at time 0, plus the integral of the voltage applied across that inductor from time 0, at the initial conditions, through to the present time t. Divided by the inductance. So electrical engineers spend a lot of time looking at equations and then translating them into schematic representation of what's going on. So a way of representing this equation here as a schematic, as an electrical circuit, is to think of a voltage source here, which might vary with time, but in this instance we're going to just assume it's a constant voltage, capital V. We're looking at the current that is circulating in the circuit, and the current that circulates depends on what is connected to this voltage, which is, in this case, just an inductor, just a simple inductor. So what happens is I start the circuit up at time 0, and let's, for the sake of argument, say that maybe there was a current flowing initially. It doesn't have to be 0. So we've got a current at time 0, and then I apply this voltage. Because I'm applying a constant voltage across the inductor, this is constant, the inductance is constant, and so di dt must be a constant. That is, we have a constant rate of change. So the current isn't constant, but the rate of change is. And so, of course, we just get a slope ramping up forever and ever and ever until we switch the circuit off. Okay? So this is what an inductor does, and it turns out it's a sort of fundamental component in our component zoo, as I tend to call it, from which all electrical circuits are eventually built. Okay? So it's all very well saying there is this thing called an inductor and it follows this equation. Of course, we're engineers. We don't just think about the mathematics of the thing, although that can be very useful. We want to know how to actually build this thing. And as you probably have already seen or perhaps guessed, an inductor is just a coil of wire, really, when you get down to it. And we can even see in the symbol, that kind of looks, if you squint right, that looks a bit like a coil of wire. But in practical circuits, we don't tend to just see coils of wire sort of hanging out in our circuits. If you take apart a computer, you do not just see a bare coils of wire, although maybe in some situations you might. Often we see a coil of wire wrapped around a core, a magnetic core of some description. And so this might be a kind of diagrammatic representation of what we see, but in practice, when we actually get down to the nuts and bolts and we're actually building circuits, you might see an object that looked a bit like this. And so this is a power inductor, sort of about that size, relatively high current. You can see it's got quite thick copper. You can see two terminals of which we might apply a voltage, and then we'll get a current flowing through that coil. Right? And although we won't cover it in this lecture, the core is very, very important for constraining the magnetic field. Otherwise, your magnetic field tends to spray everywhere, and this becomes a problem when you're building compact circuits. Okay, so to understand inductors, we need to understand currents and magnetic fields and how they interact. Now, I'm sure many of you, again, have seen this sort of diagram in physics. The black line is a conductor with a current flowing upwards. Around that wire, we develop a magnetic field. And we call this magnetic field the H field, capital H. And it has a strength that varies with distance away from the wire. It drops off with a 1/r relationship. So what this means is the field is certainly not the same everywhere. Close to the wire, it's stronger, and further away from the wire, it's weaker, and it falls off as 1/r. Thank you. And it's circulating, so it doesn't point in the same direction everywhere. It points tangential to these circles that occur around this wire. So the equation for the strength of the magnetic field, that is the length of the arrows, is just I over 2 pi r, where I is the current flowing through the wire. So it's really important, and this would make more sense if you'd already been to my lectures on capacitors, where we see that the field strength in most capacitor structures is constant everywhere, and this makes the problems easy to solve. That's not true for most magnetic problems. Something to work here. Now, you've probably come across the right-hand rule before, which helps us understand the direction of rotation, okay, or direction of circulation, I should say, around the wire. Okay. So when we start coiling wire, we understand, or that the idea of coiling the wire is we're going to concentrate the magnetic field somehow, right? And it's worth us exploring graphically how that process of concentration occurs, right? And so when I have a 3D coil of wire, engineers often express these sort of arrangements by sort of slicing through the plane of the page. And so you often see diagrams that look like this, where each one of these represents a current carrying conductor. The dot here means the current is flowing out of the page towards you, looping out, and then coming back down through the cross. So the way you think of it is like you're looking, unfortunately, an arrow zooming towards you in this case, and here, much nicer, the arrow zooming away from you into the page, right? And so I'll just state it. The field in a solenoid or a coil of wire looks something like this. Critically, it's got a very constant field strength in the center of the solenoid. And I want you to understand qualitatively why it is constant in the center and not varying very much, at least. Okay? So if I slice through this, because the thing is symmetric, radially symmetric, I get this, I can just slice through it, and I've kind of captured all the information I like. But you've got to remember, this is a three-dimensional field, not just a flat thing. Okay. Also important to remember that just because I've drawn these lines broken does not mean in truth they really are broken. I just ran out of space. They should loop back on one another and reconnect on the other side. Okay. So why is the strength? How can we use our understanding of basic magnetic fields, so the circulating fields, and turn that into a constant field strength in the middle? Well, think of it like this. Each one of these wires has its own circulating field, and we can see that, for example, between two wires here, those circulations are in opposite directions. One, it's coming up, the other's coming down, they're the same strength, and so we would expect, or roughly the same strength, and so we would expect them to cancel out. So for example, we do not expect to see much field between two conductors. Okay, it's a good starting point. In the center of the solenoid, of course, the fields are all pointing in the same direction, so we can immediately see that they're going to reinforce in the center and cancel between the wires. So if we kind of just draw more field lines away from the conductors, we see that, yes, they're all starting to concentrate in the middle, all pointing, all reinforcing in the center of the inductor. Okay, great. Right, so the important thing is that the field from this conductor, for example, is weakening as we go in this direction. So it's strong here, weakening in this direction, and the field here is strong here and weakening as we go in this direction, and they mostly combine to produce an almost perfectly uniform field strength. Now the details of how that happens mathematically I won't go into here, but this is a graphical representation of that, which is enough to build our understanding for now. So this leads us on to Ampere's law, which is expressed in vector calculus, right? So some of you may have come across that. You'll certainly study it lots when you come into the first year in engineering science. But the important thing to realize is that when I draw a capital H in bold, I mean that this is a vector field. So a field is something that takes a value at every point in space. A vector field is a field that takes a value and a direction at every point in space. So we can imagine that if I said, what is the H field at this point here in space? It could be an arrow pointing in this direction with a certain length. And that direction and strength might be different for the H field here, for example. Right. So this is looking at the whole field, H. And the way we express, or the relationship between this field and the problem setup, that is the number of terms and the number of turns, the number of coils of wire, and the current flowing in that wire, is expressed by this, right? And so, in words, what Ampere's law says is the integral of the magnetic field along a closed path, so we're going to do some sort of path integral, is equal exactly to the current enclosed by that path, the total current enclosed by that path. Now, what do we mean by total current? Well, it's this concept of, if I've got, I don't know how many wires have I got here, 8 wires carrying 1 amp each, if I drew a path around this whole section, I would have a total current of Ni, that is 1 times, N is 8, I is 1, so 8 ampere turns, or 8 amps in this enclosed path. So here is the clever bit, right? The only thing we have a freedom to choose once we've kind of drawn this setup and found the bit of maths is to choose the path that we're going to integrate along. Right? Now I'm going to choose a path that goes right through the middle of that solenoid and then loops round really, really far away from the solenoid. You've got to imagine it almost stretching off to infinity. So this is our path C for our line integral here. Right? So we're going to integrate all around the loop. What do we mean? Well, we're just going to sum up the H field that points along that line as we go all around that loop. Okay? And if we do that, well, I mean, it could be pretty tedious if this line extends off to infinity because, you'd have to count it all around, messy. But luckily, we can say, after a set of simplifications, that really the field out here away from the inductor is pretty weak, right? So maybe we could ignore the path that's far away from the inductor. Okay, one assumption. And if we further make the assumption that this solenoid is really, really long and also quite thin, or long and thin, then perhaps the stuff that's going on here where the field is kind of bending away, we can kind of ignore, right? Because most of the action, most of the value of the integral is going to be built up in the center of the solenoid along this strip. We can ignore the contribution here, and then the field is really weak over here, so we can ignore all the contributions around here. So we argue really that all we have to do is integrate along this path. And we've already established that the field strength is pretty much constant in the center, and so we've got all the parts of that equation pinned down, right? And so what we can say is that to evaluate this integral, I only need to evaluate the H field along this path. Even better, because the field is pointing in the same direction of the path, I don't even have to worry about the direction, so I drop the vector dependence and just turn this into a scalar H. So then I have this object, I'm integrating H along this path, I get Hx evaluated between 0 and L, 0 to L, I get HL equals to Ni. And from this, if I know Ni and L, I can figure out the magnetic field strength without having to do any nasty geometry calculations which were implied by the previous slide when I had all those circles adding up, which is a neat result, right? So often you start with a general law, essentially a physical law, and then we use that as an engineer to build up an understanding of the particular structures we are interested in. Right? So we're applying physics to build useful things, right? Which leads us on to useful things, or possibly useful things at any rate. Now I am running, of course, behind, as is natural in any academic presentation, so I'll try and make this swift. Right. So this is to try and show you that the stuff you learn in the first year is the foundation of complicated physical systems which are actually used in the real world. Now it may not feel like that when you're studying them the first time, but I promise you I went through the same thing and I definitely use this stuff every day, so it's important as far as I'm concerned at any rate. So this is something that my research group and others in the department have been working on over the last 2 or 3 years. So the first thing I'll say is that this is quite big stuff, right? If you sit on a jet airliner, you look out the window at the jet engine, you're looking at an engine that can produce something like 30 megawatts. It's quite a lot of power, right? Now in my group we have built a device which can produce pulses of power equal to 15 megawatts, so about half the continuous output of a large jet engine. Now of course the devil is in the detail. Continuous is a very different thing from peak, but nevertheless these two power levels are comparable. So we are building a device to stimulate the brain magnetically, which has to produce peak powers of 15 megawatts to get the intended effect. And on the face of it, that's quite scary. Would you let the jet engine in anywhere near your head, kind of thing, right? So presumably not. Would you let my research group's piece of electronics anywhere near your head? I'll leave you to, but you can keep that one to yourself, perhaps. Yeah. Okay. Right. So to just give you an example of what we're doing, we are producing pulses or current pulses in a coil, which have a magnitude of something like 6,000 amps. We're using voltages of 2,000 to 3,000 volts. So here you can see a plot of the current flowing in the coil and the voltage applied to the coil. These pulses last something like 400 microseconds, which is obviously a very, very short period of time. Okay? And this is why we get very high peak powers, because we multiply the peak current and the peak voltage, VI equals P. But we're only applying them for very, very short periods of time. So this is how we can do it in a box that's relatively small. And then the business end of this machine is this coil, right? And to link it back to the previous lecture, inside this coil, or inside inside this object here are 2 coils of wire, just like the solenoid I showed you, although a bit flatter, and it drives a magnetic field or a magnetic flux down through one of these circles, up through the other circle, and that magnetic field intersects the brain. So you bring this coil close to the head and the magnetic field passes through the brain. We can do interesting calculations and say, well, if you take my lectures, we will show that the energy stored in an inductance is half Li squared. If we take the inductance of this coil, it's about 15 microhenries. Take the peak current, 5,000 amps. The peak energy that is stored in the magnetic field is about getting on for 200 joules, okay, which is a significant amount of energy delivered over a short period of time. Here's a better picture, right? So we take this coil, we put it next to the brain, and the field intersects the brain, and we'll get an effect, right? We'll talk a bit about that effect over the next few slides, right? So bringing it back to the engineering, what have we got? Well, we've got a glorified voltage source linked to a big coil. We're going to drive a magnetic flux through that coil. That flux is going to intersect someone's brain. It's going to induce a voltage in the brain. it's a transformer, and that voltage in the brain is going to cause a current to flow in the brain, and that current is going to modify the behavior of the brain, either suppress or activate neurons and have a medical effect, okay? Which maybe we'll come on to a bit later, talking about the engineering here rather than the medicine. So that's the coil. The magnetic field passes through the skull, pretty important part of the deal, and then the brain is the receiving coil, if you like. I'm going to try and show you how we can use some of the theory we've just seen and model this system. Okay. So it's interesting to think about how much current does actually flow in the brain when we apply one of these pulses. And of course, that's not an easy question to answer precisely, because the brain is a very complex structure. What does it even mean to say what is the current that flows in the brain? Because, you know, brain isn't a wire, right? It's a lump mass. You know, not an easy question to answer, but let's have a go just because it's interesting, right? So I can tell you that the peak flux density produced by the coil when the system is working flat out is about 3 Tesla, which is a large, very strong magnetic field. Now, if we take the general version of Faraday's law that says the curl of the electric field, so this is the voltage induced in the brain, you can think of the E as the electric field, is equal to the partial derivative of the flux, that's the B, magnetic flux, peaking at 3 Tesla, by dt. Right? So, without getting into the sort of nuts and bolts of the vector calculus, we can make some relatively simple approximations and say that the strength of the electric field we produce is equal to roughly the radius of the effect, looking at the rate of multiplied by the rate of change of the field, and this will give us the electric field strength, the magnitude of the electric field in the brain. So the distances involved are about 30 millimeters, you know, between the coil and then goes through your skull, through various bits of tissue, and then actually starts interacting with the brain. And we've established that we had a 3 Tesla peak flux density at the coil, but this is attenuated to something like 1 Tesla by the time it gets to your brain. And so we can vary, and the pulse length is about 200 microseconds, and then we can very approximately work out the field strength as 150 volts per meter. Fine. What does this actually mean? Well, if you go and look in the literature, you can find resistivity for the brain. So this is the resistance per unit area of resistivity, the bulk resistivity of the brain itself, and it comes out to about 10 ohm meters. Okay, fine. We'll let the medics figure that out for us, and therefore we can say that the current density in the brain is equal to the electric field strength divided by the resistivity. So this is just like V over R, really. And we can say, well, this comes out to about 15 microamps per millimeter. Okay? Might mean something to me, and maybe it does to you. Think of the equivalent, right? So if you've got a kettle at home, this thing might draw about 10 amps, right, from the mains. It probably has 1 millimeter squared copper wire. So that would imply that the current in a kettle cord was about 10 amps per millimeter squared. So this is about 1 million times weaker, give or take, right? So that's a good thing, right? Because you wouldn't want the kettle cord in your brain, presumably, right? But, you know, it's this order of magnitude. Engineers spend a lot of their time worrying about orders of magnitude rather than every decimal place, right? Okay, so following this through, let's think about how much energy is transferred to the brain. Remember I said this large piece of electronics was putting 200 joules in. Well, if we take, skipping ahead there, I can work out the power dissipated in the brain by doing essentially I squared R, right? Looking at the power dissipated. And I end up with about 300 milliwatts. So sort of the energy you'd need to light an LED, or the power you'd need to light an LED to a decent brightness, but not too much. And the length of time that this takes, remember we said about 200 microseconds, 200, 400 microseconds. Well, we can multiply power by time and get 100 microjoules. So 100 microjoules delivered to the brain by this one pulse. Right. Okay, so we've now got all the numbers we need. Think about the power transfer efficacy of this system. I said we're putting 15 megawatts in peak, and I'm saying we're getting 300 milliwatts of effect in the brain. That is not a very big number. Fine. Think about how much energy we're transferring. Okay, we've got 100 microjoules into the brain, dumped into the brain, but I had to put 188 joules into the coil in the first place to, get that to happen. Also not a very big number. No, it's a bit bigger though than the power transfer efficacy. Actually, in practice, because our electronics recovers a lot of the energy as we reduce the magnetic field, this number is quite a lot smaller actually. The energy we lose every pulse is only about 20 joules, but when you're talking about numbers with this many zeros, does it really matter, is the question. So, I hope that was vaguely interesting in a kind of slightly mathsy way. Of course, whenever you do an analysis, what we might call a back-of-the-envelope model here, you have to attach big warnings to it and say, well, we're only trying to get a feel for the size of the problem. These numbers could be an order of magnitude out in either direction. The point is we do understand that TMS is not an efficient process, and this is why I have a huge box of electronics to make relatively small effects occur in the brain. Right. Just to give you a quick overview of the actual hardware, well, this is the XTMS unit we built. So TMS, I probably should have said this, stands for Transcranial Magnetic Stimulation. Our system can develop these large pulses in a very controlled way, which means we can really tailor therapies depending on the requirements of the patient and the particular thing we're trying to achieve. We've got lots of quite complicated high-power electronics, a lot of control software to run this system in a safe and an effective manner. We've got, for example, a large output filter, which is something that, for example, you'd be able to design after your first year at the university. You would understand how you could put together at least some parts of this system. By the time you got to your fourth year and then maybe studied for a PhD, you'll be able to build things like this. Oh, bit of zoom in. So this is sort of the core power module. There are 3 of these in the system. You can see it's relatively complicated. You can see the large energy storage capacitors just hidden here. These are large power transistors, all connected together with large copper bus bars to carry this very high peak current. Okay, so in summary, TMS, transcranial magnetic stimulation. We make all this effort because we don't want to drill a hole in someone's skull and put in a wire, right? Which is another way to do it, but clearly that's quite invasive, whereas waving a coil around someone's head is perhaps scary but not invasive, right? An observation that energy in electronics tends to be very cheap. Surgeons, on the other hand, are not. This is a very crude technology. We're really just dumping this energy into the brain and hoping for an effect. But these new generations of machine, one of which we've developed in our group, are making this a bit more tailored, a bit more precise, and that's very exciting. This could be a really important therapy in the future. What's really nice about this is it takes technologies developed for example, electric vehicles, wind turbines, that kind of thing, high power transistors, and it moves them into the medical space, right? So this is a sort of the march of technology has allowed us to build machines like this relatively easily. We wouldn't have been able to do this 10, 15, 20 years ago. As always, we expect this to continue. When you guys are building these pieces of equipment, once I've retired, you'll be building them smaller and better, I am sure. And that is exciting for an engineer, I think. Just a quick shout out to the team. Myself and my postdoc, also a colleague in the Institute of Biomedical Engineering, Tim Dennison, who's done a lot of work on this as well. I'll point out, all of these people, everyone here studied some sort of electrical and electronic engineering at university, and they've all gone on to have very interesting careers so far. So you're making a good choice by choosing engineering science, I think. Right, thank you.